Hey Carly.
Hey Wes.
Today let's talk about multiple linear regression Python. We know that linear regression has a list of independent variables, and that's all we need to change. So before we talked about our list of independent variables, we talked about just one variable, the caret weight. But I have a prediction. I predict that when we look at diamonds, that it's not just the caret weight, it's not just how big the diamond is in weight, but I think the surface of the diamond that you can see is going to make a diamond more valuable. And that surface of the diamond you can see is known as the table of the diamond. So if a diamond is really tall but doesn't have a very big surface, it's going to have a smaller table. But if it's a kind of a flat diamond that has a big surface, it's going to have a larger table. And I think because most people just see the top of a ring, they're going to potentially want to see a bigger diamond that they can see. So I have a prediction that table might be a good factor to add as an independent variable to predict price. So let's go ahead and do this. So I want to use both the weight and the table, the large flat surface you see when looking at a diamond, to predict its price. So in my linear regression model, I'm going to use the caret and the table. So there's a couple things that I have here, just so we can start a fresh notebook, is I need to have first a data frame loaded up, because this implies I'm using the data.
Just did that.
So you imported pandas PD and loaded the diamonds data set.
Yep.
The second thing I need to do is get the linear regression library going, or the linear regression model. So I'm going to write from sklearn.linear_model import linear regression. And did that work?
Yes.
Awesome. And then I'm going to go ahead and create the model by saying model is equal to linear regression with no options. So open close parentheses.
Got it.
And now I can go ahead and fit my model. But the model.fit, I'm going to now have inside of my independent variables, I'm going to have df at, and then I need to list all of my independent variables. So here my list is going to contain caret, and it's going to contain table. The two different variables that I think may help me predict the price. So now we've got a puzzle. So I actually am interested in finding out what is the difference in error between these two situations. So Carly, I think you've created a model using the multiple linear regression using model.
Called
right?
model.
Called
yes.
model. And I'm going to go ahead and create a second model using simple linear regression. So simple linear regression is just one variable. So I'm going to call this simple model. So I have now a second variable. I've got model, which is my complex model using multiple linear regression. And I have simple model, which is simple linear regression. And that is going to be we first have to initialize a new model. So simple model is equal to a linear regression. And now I'm going to do simple model dot fit, open parentheses, df at, and then I need to list my independent variables. That's just going to be caret. So the simple model is only going to use caret to predict the price, and it's going to predict df at price.
All right, wait, I just did it, and I have model and simple model.
Awesome. So we also found the prediction using multiple linear regression. We've already done that up here, so we have that done. Carly's added in model. We did that earlier. So the model variable contains our multiple linear regression. And then I want to calculate the absolute value of errors in both simple model and model.
Ooh, okay.
So I want to calculate all of the errors. So Carly, you always say that you calculate errors. The error is equal to the actual
minus predicted.
Actual minus prediction. So the first thing we need to do is we need to use the models to create a predicted price for the various different diamonds. So I'm going to have us say df dot price simple. I'm going to say simple p for simple prediction. So price underscore simple p is our simple prediction, and that's going to be equal to model, or is going to be equal to our simple model dot predict And then our simple model only has df at, and then a list of our independent variables. Our independent variable is just caret. For our simple model, close square bracket again, close parentheses. And that should add a simple prediction to our data frame. And now I want to do also df at price underscore multiple, multi-p, I'll call it, is equal to model dot predict, now using the complicated model. And we're going to predict that based on the inputs df at, and then I'm going to give our list, which includes caret, followed by table, close square brackets, close parentheses.
Got it.
And then if we do df, we should see we have both the price and the predictions.
Yes, I have both of them.
Awesome. So now I want to find out what is the error. So I'm going to do simple error and multi-error. So this is really simple. So we can do df at error underscore simple for our simple error. And that is going to be the actual price. So that's going to be df at price minus our df at price underscore simple p for simple prediction. And that's going to create our error for our simple prediction. And then our error for our multiple linear regression, I'm going to do df at error multi. And that is going to be df of price minus df of price multi-p. So this gets to the importance of naming your columns correctly, because we're now adding a whole bunch of extra columns. I always say what the variable is first, and then have an underscore and kind of give the details of what's special about it. So I always say my original column was price, so it's price underscore something.
Got it.
My original column's error. So I have a very kind of conventional way that I'm going to name all of my variables and all of my column names, so that even if I see this data frame later, I'm going to have an understanding what these variables are. So if you see df, we should have a lot of extra columns now.
Yes, we do. We have 4 extra.
So I may want to know, so one thing I want to check out is just do df.sum and make sure in both simple linear regression and complex linear regression or multiple linear regression, we have 0 in our error columns.
Yes, we definitely do.
So at this point, we can now do an RMSE, or I'm going to just go ahead and use a average absolute error. So I'm going to go ahead and create an absolute value column that's just going to take the absolute value of the error. So I'm going to just say df of abs error underscore simple is equal to abs parentheses df of error underscore simple. And then the second thing I'm going to do is I'm going to finally do df at abs error multi is equal to the absolute value, or abs, of df at error underscore multi. So what I'm doing is I'm taking the absolute value of both of these errors and creating new columns. And now I want to know so what we have is every single row, if we look at df, we should have every single row now has an absolute error using simple linear regression and an absolute error using multiple linear regression as the last 2 columns.
Yep, got that.
And they should both be all positive numbers, even if the error was negative.
Yes.
So now all I want to know is what is the average absolute error. So the average is simply the mean. So Carly, if you do df.mean, what do you get?
So I get, so the absolute error for simple is 1.007463.
463 times 10.
Instead of the third.
Yep.
And then for the multi, it is 1.000328 times 10 to the negative third, or 10 to the positive third.
Positive third. So 10 to the positive third means that basically we're thousands. I'm not even sure why it gave us into.
Yeah.
So removing that scientific notation, that's $1,007.46 versus $1,000.38 or 33 cents. So the multiple regression, we got a small, tiny bit of improvement.
Slight bit of improvement.
The difference between these is 7.46 minus 0.33. So the difference in error is right about $7. So $7.13 it looks like. So out of $1,000 of error, by adding additional variable, we get a tiny bit of improvement. But my prediction was pretty wrong.
Yeah, it wasn't that much improvement.
Yeah, the table didn't really help us create a better model to increase our productivity or our prediction amount for the price. So if you think about why this matters and why we care about doing this, is if you imagine you are running a diamond mine, you might say, should I measure the weight of all the diamonds, or should I also measure the weight and the table of all the diamonds if I really want to know a good estimate of what that diamond might sell for? And from this analysis, we see that it didn't help us very much knowing the table. There may be other factors that we might want to analyze, and I know for a fact that the color and the clarity of a diamond matters a lot in the price of the diamond. So those are factors that we may want to use in our regression. But we see that simply adding multiple values to do multiple linear regression many times doesn't actually help us predict a better price.
Yeah, and it might actually be more work than it's worth to actually take all those measurements.
Exactly, especially when you think that a human probably has to be measuring that diamond, and that costs money to employ that person and to take all of those measurements, to record all those measurements. So there's a real cost to actually adding more data.
Cost-benefit analysis.
Exactly. So this gives you a little insight of how to use multiple linear regression and when you might want to actually decide that multiple linear regression is worth it, or when you can get away with simple linear regression. Because simple linear regression is really, really powerful and often will get you a really great result from many different data sets.